Well, good morning, good afternoon, good evening, wherever you are in the world. My name's Steve Rogers. I'm Head of Commercialisation at Glycerol, and I'm here to talk to you today about the potential for using sugarcane residues. Those are the tops and trash, sometimes known as, from the sugarcane harvest, and how that can be used to help decarbonise the marine sector. Before I go on, I would like to just congratulate the BBEST organisers for putting on this conference in what are incredibly difficult circumstances. So thank them for the opportunity of talking to you all today and congratulate them for still managing to find a way to put this conference together. Before I start, I will just, there's a safe harbour statement. There's been a few announcements around Glycerol recently, so it's important that you are aware of this disclaimer. So what am I going to talk about today? Really, to start with, I'm just going to set the scene, sort of say why this could be of interest, especially in Brazil, to the sugar industry, outline a bit about what the opportunity is, and then talk about why shipping could be a good opportunity. And why, as the use of biofuels expands into those heavier industries, those that are harder to decarbonise, i.e. the ones that haven't been typical area for ethanol, this is a good opportunity. Then we look at the benefits of hydrothermal liquefaction oils over pyrolysis oils, and then talk specifically about the project that we've got running in the Burdekin, which is a major sugar growing area in Australia, and then touch on the Glycerol process. So why? Well, for everyone who's interested in this field, I suppose it takes no real explaining. We're still using over 100 million barrels of oil a day, and that's despite the needs for us to rapidly decarbonise, and as we know, that has to happen this decade. So we have 10 years to rapidly accelerate the use of non-fossil fuels. And as we can see here, the IEA projections are saying that if we are to achieve this decarbonisation, we need to tackle some of those areas which traditionally haven't been able to be addressed by biofuels, and by that's the maritime, the aviation, and the heavy road sectors. And so you can see that why this is expanding. And clearly in Brazil, you've done a great job to date in using sugar for making ethanol. But what we can clearly see is there are opportunities in the areas which have traditionally been used for diesel and also for jet fuel. So why do I think the marine is a good opportunity to start? And there are two sort of macro factors here which are sort of driving this potential opportunity. One is that whilst the sulfur levels have sort of been coming down through sulfur cap reductions introduced by the IMO, the International Maritime Organization, there was a big sort of almost seismic shift in the industry at the start of last year, in January 2020. And that came about with the introduction of the 0.5% sulfur limit, or the very low sulfur fuel oil requirement. And that drove down the sulfur requirements in the fuels that are used from 3.5% to 0.5%. And that had major implications for the shipping industry. Now, the opportunity that presents for biofuels is that typically biofuels are low in sulfur. And so there's an opportunity there that if we can use biofuels in this space, then that addresses that need. The other thing that we've seen that's happened as a consequence of this is that these new fuels that have been introduced are a significantly higher price than the old bunker fuel there, the IFO 380. And so what's happened is those prices of the low sulfur fuel oil, where it is available, are now trending up to just under that, under marine gas oil. And the further you get away from the major hubs, the higher that premium is. And so in our part of the world there, you can see that there's good prices for biofuels there. These are US dollar prices, but you can see in Melbourne in Australia, $640 a tonne. That's nearly 850 Australian dollars. And at those prices, these fuels start to look commercial, and it's of interest without subsidies. The other big factor that's happening here is that greenhouse gas emissions have to reduce in the maritime sector. And so the IMO has come out with these ambitious targets for them to reduce greenhouse gas emissions as well. And of course, again, using biofuels is an area that can help that. So we can see these two key factors driving the maritime industry potentially to a much higher adoption of biofuels. And so we see that some organisations have decided to take a leadership role in this regard. And Maersk, who's the world's largest shipping company, has taken a stance that it will embrace this challenge and has made a commitment that it will reduce its greenhouse gas emissions by 60% relative to 2008 levels by 2030. That's a big ask, but they're very serious about it. And as you can see there, they're already making good inroads in that regard. But if you actually look at some of the work that they've actually done, and again, I borrowed this slide from Maersk, you can see they've looked at all of the potential ways that they can actually decarbonise from biofuels at the top down to what they call these moonshot projects at the bottom, i.e. converting boats to using ammonia and hydrogen. But you can see on the right-hand side of the slide there, what they've also done is they've evaluated what the cost implications are of implementing these changes. And so for the benefit of the biofuels industry, is you can see that by using biofuels, because of the fact that you can use the existing infrastructure that exists on board the vessels, and because these big engines that exist within these big two-stroke diesel engines can basically burn more or less anything as long as you can get it into the engines, then the potential to be able to use these biofuels is high. And so again, this is a really good opportunity for us as to why we should be exploiting and pursuing this opportunity in the marine space. And then if we actually, so this is coming to the point about why we now need to start looking at what we call the lignocellulosic feedstocks, those that typically fit in this advanced biofuel space. We can see that the traditional place where biodiesel or HBO has been made is by using these fats, oils and greases, the fog feedstocks. But we can see here that the cost of these products, and this is a Neste slide, is considerable. With prices, trending up towards $1,000 a tonne US just for the feedstock. So clearly, if you're able to be in a situation where you can be aggregating other feedstocks at a price, significantly less than that, so $50 to $80 a tonne, you're in a situation whereby you have a significant advantage over where you're having to use these feedstocks, which are going to become an increasing demand as the needs for sustainable aviation fuel and others start sucking more and more of these feedstocks up. So again, reflecting back on these prices, you can see that this is a really good opportunity for second-gen biofuels using these crappie residues. And so in this space, if this is sparking some interest, I would commend this publication to you. It was a publication done by the Oak Ridge, the National Labs in the US, and they looked at a variety of different feedstocks that could be suitable to be used as biofuels in the marine space. And here you can see them all there. And on the right of the slide that I've highlighted, you can see that hydrothermal liquefaction biocrude is there, and it has a value of about double that's available from pyrolysis oils. So it is a high energy density feedstock, and it's a feedstock which can be used more or less ex-reactor, i.e. it does not have to go through refineries to be able to be miscible or used on the vessels. There's more work that needs to be done. There are issues here around its density, and we clearly have to look at how we would actually integrate it into the fuel systems on board the vessels. But this is very promising, and with the shipping industry, willing to pay based on energy content. Again, this is another reason why this is a good opportunity to look at HTL oils for the marine sector. Again, this is just another piece of work from the US DOE, where they're actually looking at the energy density of the fuels, and again, you can see there that hydrothermal liquefaction biocrudes, perform well in terms of the energy density, and the energy is clearly what the marine industry is after. So then if we actually look at the opportunity that exists in the sugar space, we can see that there's almost 2 billion tonnes of sugarcane a year. If we say that about 10% of this is the tops and trash or the residues, so that's earning up towards 200 million tonnes a year of this feedstock available. If we say that there's about half of that can be left on the field, and from a Brazilian context, that means there's about 40 million tonnes worth of potential feedstock, and that could convert over to about 10 million tonnes of fuel. So there you can see that, with a use of 4.5 million tonnes per annum in terms of fuel oil, Brazil could become self-reliant in terms of those fuels, and indeed export them to these other markets. And globally, where you've got a 350 megaton opportunity, we can see that the sugarcane residues alone could account for 7% of the feedstock. Just moving on to the Burdekin project that we're looking at here, again, the key drivers here is actually looking at the fires that exist in the Burdekin each year, and this is spewing down ash onto the Great Barrier Reef, something that wants to stop. And we can see that there's about 1 billion tonnes of feedstock available there in that region, with over 4 million about 4 million tonnes of residue available in that area. And the farmers there have been developing some innovative ways that they can do single pass harvesting, so they're able to actually harvest the billet in one go and then separate the billets from the tops and trash as they're brought into the mills. So using the existing infrastructure there to be able to achieve that. What that then means is when it comes to our facility, we take the tops and trash, we convert it using the hydrothermal liquefaction technology, which is basically nothing more than water, just normal water at high temperatures and under pressure. And what that acts as desulfurizing agent to break down the residues and to produce the biocrude. The biocrude can be processed co-processed in traditional refineries into a traditional range of products, or it can be used in this form for direct use in the maritime sector. Glycerol, we've been scaling our technology up over the past 12 years, so we're not the new boys on the block here. We've been doing this diligently, carefully, moving up through the different generations of the projects. We have a significant project underway in Canada working on woody residues with Canfor Pulp, the Canada's largest pulp and paper company. And we are the world leaders in terms of hydrothermal liquefaction. So from our perspective, we know what we're doing. This is a very real opportunity that's here. So in summary, what we're offering here is an opportunity to the sugar industry to monetize this waste, potentially to use, if you're still burning these residues, to produce another stream through carbon offsets, to a market in marine that's really looking for solutions in this space. They're looking for low carbon solutions, and they are able to burn fuels such as this. hydrothermal liquefaction really provides a great opportunity to help bootstrap large volumes of advanced biofuels into the market, and Glycerol are the world leaders in this space. I'd like to thank again you for listening and for the opportunity from the organisers to present at the conference. If this is of any interest to you or you'd like to hear more, my contact details are here. And thanks again, and g'day from Australia.
Hi everyone. First of all, I'd like to thank you to be here with you. It's a pleasure for me. I'd like to thank you, BBEST, for the opportunity to show Hytron synergies and Hytron technologies for the production of hydrogen from ethanol and renewables. I am Gabriel Lopes, Commercial Director of Hytron. So, Hytron is a company, a high-tech company from Brazil, focused in solutions for hydrogen production and purification. Talking a little bit about our history, I am a co-founder of Hytron. We founded Hytron in 2003 as a spin-off from the hydrogen laboratory at Unicamp, the University of Campinas. One of the main important universities from Latin America. Hytron was born strong in R&D activity and focused in innovative and applied solutions for hydrogen. We have a lot of expertise in hydrogen production and alternative energy systems. Our specialists is prepared to work with multidisciplinary issues, and we have in our team PhDs, masters, and specialists. We are technology developers, and our main acknowledgement is in system design, integration, and supervision of our solutions. In 2015, we built our new headquarters, and with these headquarters in Sumaré, next to Campinas in São Paulo, we created a facility dedicated to R&D and fabrication of our equipments. Our expertise is in energy sector, industrial gases, and R&D. Very recently, Hytron was acquired for NEA Group, a German group with almost 200 years, specialized in hydrogen compressors and in gas compressors, is a leader of gas compressors systems worldwide. And with this partnership, this relationship with Hytron, we could provide the total solutions from hydrogen production, compressor, storage, providing for our client the total solutions involved in hydrogen. The NEA Group have presence in 10 strategic countries with 28 companies. Here in Brazil, we are with 2 facilities, one in Belo Horizonte and another one in Sumaré, it's Hytron. In Belo Horizonte is NEA Brazil, and in Sumaré, Hytron, in São Paulo. The NEA Group has something like 1,200 employees around the world, and consolidate sales in 2020 about 230 million euros. We have 5 business units, starting with compressor solutions. We already have process solutions, digital solutions, and energy solutions. Hytron is inside of this energy solutions business unity. But we aren't alone. because we have another companies inside this business unity. Here we can see all the value chain, the presence of NEA Group in all the value chain of hydrogen. And we can start with the biomethane or the biogas production when the NEA Group have the Arcanum company, and providing solutions from compressors. The NEA Group can provide this biomethane for industrial use, and with Hydron we can produce hydrogen from various instruments. So we can provide hydrogen from electrolysis, from hydrogen from natural gas reformer or biomethane reformers, and from the ethanol. With the hydrogen production, we can compress this hydrogen for uses, and we can use this hydrogen to compress this hydrogen to provide the hydrogen logistics, and we can provide the hydrogen storage or gas storage and the hydrogen use for mobility, and when the client needs, we can provide electricity again from hydrogen. Here we have our experts team. Antônio, Cristiano, me, Diego, and João Carlos Camargo. We are the co-founders of Hydron, and we are directors of Hydron with this NEA acquisition. Talking a little bit about our products, we have 5 kinds of products. We can provide, like I told you, the electrolyzer from PEM technology or alkaline electrolysis. We have our own technology to provide hydrogen from natural gas, biogas, and ethanol reformer. And we have our own technology to purification of gas and purification of hydrogen too, with our PSA systems. With this, Hydron is inside of various kind of hydrogen production. We can start producing gray hydrogen from natural gas, blue hydrogen when we can use the CO2 capture, or the green hydrogen when we are talking about electrolysis systems from renewables, ethanol, and biomethane. Here we have an example of our equipment. Here we have electrolyzer, PEM electrolyzer from Hydron, next to the wind farm and the PV farm, producing hydrogen from renewables in these intermittent forms, storing this hydrogen and producing electricity from this hydrogen. Here you can see a bigger equipment. Here we are talking about our PEM electrolyzer for a 5 megawatt plant to produce hydrogen, 1,000 cubic meters of hydrogen per hour. But our focus today is our reformers. Talking a little bit more about the reformers, we have here the system's attributes. We can provide per model something like 315 cubic meters of hydrogen per hour. We work with total solutions, the real turnkey solutions from this kind of equipments. We have the feed treatment, the PSA system the thermal management, the controls, etc. And we can provide up to 6.9 of purity, when we can provide hydrogen with 99 duc 9999% of purity, working pressure up to 10 bar without compressors. Here we have the technical issues of our equipment. We can see here the steam reactor, the shifts reactor, and the process water, the centralizer multi-fuel burner, and all the BOP, the balance of plant concept. But the hydrogen concept is to provide our solutions inside a container. In this case, I am showing you the biomethane used for hydrogen production. In this case, we can use something like a 4.8 cubic meters of methane to provide a kilogram of hydrogen, 35 liters of water, and 4.7 kilowatt hour per kilogram of hydrogen. In the same case, we can provide the ultra pure hydrogen for PEM fuel cells applications. Here is our focus today, because we are here in Brazil. We can talk about the use of ethanol to provide hydrogen. In this case, we need something like 7.6 liters of ethanol to produce a kilogram of hydrogen, 30 liters of water, and only 2.35 kilowatt hours per kilogram of hydrogen. We can provide either the 6.9 purity of this hydrogen. And per model, we can provide something like 750 kilograms of hydrogen per day. Here we have important informations about our reformers. We can provide, in this case, it's only a showcase here, when we have an example for 20 kilograms of hydrogen per hour case. In this case, our equipment can be supplied in a 30 feet container. The capacity is something like 20 kilograms per hour of hydrogen. The power capacity installed is around 50 kilowatt. The ethanol consumption per hour 153 liters, and the raw water consumption something like a 600 liters, 0.6 cubic meters per hour of water. For this showcase, I bring for this conversation some points, and here I am showing for you the advantage of using ethanol for hydrogen production, and we can think the ethanol as a green hydrogen carrier. And from my point of view, that's are the advantage. The fact of being a renewable fuel. So when we are talking about the ethanol, we are talking about a renewable fuel, a biofuel. It's easy to transport the ethanol, and here in Brazil it's usual to transport ethanol long distance. Brazil have the potential to maintain this importance globally as a player. Here in Brazil, we have all the value chain established, and ethanol isn't a toxic fuel. Methanol is a toxic fuel, but ethanol isn't. So we can use without some problems. The the ethanol enables the flat production of green hydrogen without intermittence. That point is very important because when we are talking about the hydrogen production, the green hydrogen production from only for renewables, as solar or wind power plants, the hydrogen production is intermittent, but when we are talking about the green hydrogen production from ethanol, we can provide flat production. So in my point of view, using both simultaneously the wind or solar sources with ethanol production, we can provide good solutions for green hydrogen production. So the ethanol is easy to store, enables local production of hydrogen close to consumption. Here in Brazil, when we are talking about the mobility, we have more than 43,000 of fuel stations around the Brazil, and 100% of these fuel stations have ethanol. So in the Brazilian case, we can provide the production of hydrogen, decentralized, and from transporting ethanol, for example. And, I believe that the same case we can think about the use of hydrogen as the ethanol as a green hydrogen carrier to export green hydrogen for other countries. Here I bring some numbers when we are talking about the ethanol production. Since for the sugarcane to produce ethanol, biogas, electricity. So here we have some case. This case I've been building this case with some specialists. Antonio Stuck from Raizen is a friend of mine, and we are studying this theme to show how is the feasibility to use the ethanol to produce hydrogen. So in this case, we have some numbers here. When we are talking about the production of ethanol, the first generation typically is produced nowadays 30 liters of ethanol from per tons of sugarcane. The second generation of ethanol can provide more, 23 liters per ton of sugarcane. We can produce biogas using the wastes from the sugarcane industry, and the number is something like 8.9 normal cubic meters of methane per tons of sugarcane, and we have the possibility to produce energy, electrical energy to something like 49 kilowatt of energy per tons of sugarcane. So when we are talking about the use of these instruments, these inputs to produce hydrogen, we can provide using this amount 40 plus 23 liters of ethanol. We can provide something like 8.28 kilograms of hydrogen per ton of sugarcane, more 1.8 kilogram of hydrogen per ton, and 0.92 kilogram of hydrogen per ton. The total amount of hydrogen is something like 11 kilogram per ton of sugarcane. That is the same to 123 cubic meters of hydrogen per ton. When we are talking about the use of the energy production, we can compare efficiency here. When we are using the Otto cycle with 25% of efficiency, the energy available in this case using only the ethanol plus the biomethane is something like 1,688 megajoule per ton of sugarcane. And when we convert this energy in electricity using 25% of efficiency, we have here something like 422 megajoule per ton of sugarcane. In the case of the fuel cell, with 50% of efficiency is a conservative number. When we are using that amount of hydrogen produced only from ethanol and biomethane, we have something like 1,215 megajoule per ton. Converting this energy in a fuel cell with 50% of efficiency, we will have something like 607 megajoule. So here we can conclude that the net energy delivered by ethanol and biomethane transformed into hydrogen using a fuel cell is 33% higher than that delivered by burning the same fuels in a Otto cycle engine. So here we have the difference, the efficiency, the difference of these technologies, and to be clear, to be clarified, to be sure that when we are talking about the production of hydrogen from renewables, we can provide this in an efficient way and with all of this advantage I told you. Thank you again for your time. Thank you for the invitation. I am here to hear from you, your debates, and discuss a little bit more about this technology. So thank you again. Bye-bye. See you at the BBEST.
Good day. Well, I would like to thank you very much, the organizing committee of BBEST 2020, for the opportunity to be here to present Niobium enhances electrocatalytic palladium activity in alkaline direct ethanol and glycerol fuel cells. This work is developed by me, Mauro Santos, with my collaborators in the Universidade Federal do ABC, Santo André, São Paulo, Brazil. Well, the global average temperature is increasing very much in the last decades. This occurs because mainly the presence of carbon dioxide in the atmosphere. This carbon dioxide is originated by the burn of fuels or of fossil fuels. And then we can see here in this figure that the temperature rise in the world relative to the 1951 to 1980 average. And in red and yellow is the increasing of the temperatures. As we can see, this problem can provoke consequences in nature, like those ones related to these figures, like burn, like desertification, and other consequences for the human beings and the animals and other kind of beings. The fuel cell can be as alternative energy source to overcome part of these problems. When you use fuel cell, we can have a device capable to convert chemical energy into electrical energy in a spontaneous way. And then we can have a maximum efficiency of 50 to 80, 30%, 83% different from the right side here, when we have the maximum efficiency of 15 to 25% in the Carnot cycle in an engine, which produces a very bad carbon dioxide amount. We have the use of fossil fuels with this engine, and then because of this, we can use the fuel cell as a possible alternative for energy sources. We have in the fuel cell a minimum emission of pollutants. When you use hydrogen as an example, we have the production of only water, because hydrogen reacts with oxygen. Cathode reduces oxygen for water, and hydrogen is oxidized for protons. And then we produce water. And then we have the minimum emission of pollutants and low noise pollution. We have also the possibility of to use ethanol and or glycerol in these cells, and then we can produce carbon dioxide. But this carbon dioxide produced is reabsorbed by the plants in the photosynthetic process, and then we have a carbon neutral cycle. But why use niobium as electrocatalyst for fuel cells, for ethanol or glycerol oxidation? Because niobium reserves in the world 103 tons. The main part of this niobium is related to the reserves of Brazil. Brazil owns 95% of the world reserve on niobium. And then it's very important to Brazil, mainly to Brazil, use the niobium as a product, a technological product in a fuel cells, as an example. But we have another question. Why use direct glycerol fuel cell? Because glycerol is a byproduct of biodiesel production, and then it can be produced by biodiesel production, is industrially available, and is easy to storage. Here we have a scheme and an example of the fuel cell using glycerol. In the cathode, we have the oxidation, we have the reduction of oxygen from the air to produce water. In the membrane that transport OH, hydroxyl ions. And in the anode, we have the oxidation of glycerol. And then in the anode, there is the oxidation of glycerol and the production of carbon dioxide. In the cathode, we have the reduction of oxygen to promote the production of hydroxide. And the global reaction, there is the production of carbon dioxide. But with the presence of hydroxide, we have the production of carbonate. And then we can generate electrical energy by the conversion of the chemical energy of this oxidation reduction reactions. But we have some challenges for alkaline direct ethanol fuel cells and alkaline direct glycerol fuel cells, like carbon-carbon bond breaking, that is too difficult to break this bond, the intermediates oxidation, CO poisoning, and high-cost catalysts like palladium and platinum catalysts. Here we have the work that I will present for you. This work was the front cover of the Chem Electrochem in 2019, the volume 21. And the title is Niobium Enhances Electrocatalytic Palladium Activity in Alkaline Direct Glycerol Fuel Cells. Well, here we have the results of this work, when we have the X-ray diffraction characterization of binary palladium niobium carbon produced by reduction method, a chemical reduction method in carbon. And we have here all the electrocatalysts studied: palladium 1, niobium 1 carbon, palladium 2, niobium 1 carbon, palladium 3, niobium 1 carbon, palladium carbon. And we can see here the peak patterns for palladium and palladium oxide. Not for niobium oxide, because niobium oxide is amorphous, and it's not here. We have here the high-resolution transmission electron microscopy of all electrocatalysts, and we can see that the particles were well distributed, and the electrocatalyst. The electrocatalyst is this part. The black points are the particles. We can see in figure 4 that the average particle diameter, the major average particle diameter is 6.9 for palladium 1, niobium 1 carbon. And here we have the possibility to see that the catalyst is well distributed in the support carbon, and that all the electrocatalysts produced nanoparticles on carbon. In this figure, we have the Hammond shift for all electrocatalysts and Hammond spectra in D and D shift regions of the electrocatalysts. And the main conclusion of these figures in the figure 5 is related to the radio of D band and G band radio. That is the highest is 1.71 is for palladium 1, niobium 1 carbon. Concerning the high amount of defects. These defects is chemical defects, like probably the oxygen as this species that can make the electrocatalyst more hydrophilic and then enhance the oxidation of glycerol. Here we have the figure 6, when we can see the cyclic flow thermograms for all of electrocatalysts studied. In green, in the curve green, we can see the palladium 1, niobium 1 carbon. When you see the highest amounts of hydrogen disorbed and adsorbed on unsorbed, the formation of the highest amounts of palladium oxide and reduction of palladium oxide. The figure 7 concerning the radiophilicity results of the contact angle tests. And this figure indicates that the higher, the lower the amount of contact angle, the value of contact angle, the higher the hydrophilicity of the surface. And then palladium 1, niobium 1 carbon, palladium 3, niobium 1 carbon are the more hydrophilic electrocatalysts. And then they are the most important electrocatalysts for glycerol oxidation in comparison to the other electrocatalysts. Chronon parameter experiment for glycerol oxidation is here. Here is a chronon parametry using glycerol and potassium hydroxide, and we can see that the higher the current, the higher the oxidation of glycerol. And then we can see that the palladium 2, niobium 1 carbon presents the higher amount of current for oxidation of glycerol. And then for this figure, we can see that this electrocatalyst is the best for catalyze the oxidation of glycerol. Like we can see here in terms of current, the current for palladium 3, niobium 1 carbon is the highest. Well, but the device that we can see that the electrocatalyst is the most important and is the most valuable and is the best for the oxidation of glycerol is the main alkaline direct glycerol fuel cell working. And then we can see here the cell voltage in function of current density or the density, power density in function of current density. We can see that the maximum power density or the maximum electrical energy produced for the electrocatalyst using the electrocatalyst palladium-1 Niobium-1 carbon is the best performance for the electrocatalyst because the maximum power density is obtained for this electrocatalyst. And then we have that we have the maximum power density with the maximum cell voltage obtained in the beginning of the curve here. And the main important result is those ones: the maximum cell voltage, 1020 millivolts, and 27 milliwatts per square centimeter. Why this electrocatalyst is the best? Because we have the bifunctional mechanism. In the case of glycerol, glycerol forms CO at the surface of palladium. And this CO poisoning the surface of palladium. But the presence of OH in the metal is niobium, can be oxidized to CO2. And then the sites are recomposed for another cycle of oxidation of glycerol. And then for this case, we have this enhancement that we can see here, that the highest maximum power density and the highest maximum cell voltage. We can compare our results with the literature, and we can see that our result is one of the most important compared to the other in the literature, because the literature is in almost the same conditions of our results, but here the comparable result is little higher than the 27, but the OCV, the onset potential, is too small compared to the potential obtained by our results. And then our results is comparable to the literature, and in fact is better than the literature. Well, to finish, we make the FT Raman for study the reaction mechanism. In this case, the main important issue is that the production of carbon dioxide. We can see here that palladium-1 Niobium-1 carbon is that produce 68% of carbonate, because carbon dioxide with hydroxide produce carbonate. And then we have the most important point that we have the transference of 14 electrons, almost 14 electrons during the glycerol oxidation. The highest the production of the carbonate, the highest the production of carbonate, the highest the transference of electrons. And in this case, we can use more electrical energy because more electron transference is obtained. Well, our conclusions: binary electrocatalyst palladium niobium were produced by borohydride method. We produced palladium niobium 1,1 carbon in mass. Contact angle indicates the high hydrophilicity of this electrocatalyst. Raman spectra conducted to obtain the more amounts of defects and oxygenated species. This electrocatalyst is superior because the results of the current, because the results of the potential, and because the results of density power density, that is the highest, with the highest onset potential for the fuel cell. this is related to the bifunctional mechanism, as I told you before. I would like to thank you very much, Luana, Edson, Bruno, Felipe, Tuani, Vitor, and Paulo for the work. The BioAim program, in which my process in FAPESP is associated. FAPESP, UFBC, CNPq, CAPES, LEM, CCNH e Programa de Pós-Graduação em Ciência e Tecnologia Química. And you for your kind attention. Thank you.
Hello everyone, my name is José Guilherme Coelho Baeta. I'm a professor at the Federal University of Minas Gerais and I'm a coordinator of the Mobility Technology Center. First of all, I would like to thank the Biofuture Summit 2 for the opportunity to be here and to speak for all of you. Right? My presentation is about the most recent R&D projects on internal combustion engines using renewable fuels developed by CTL. Well, first of all, I will introduce to you our facilities, just to give you an overview or a big picture of our facilities, and then I will go through the most recent R&D projects we've been conducting in the course of last years. Well, here on this slide, you can see a pool of laboratories that are integrated, and some of them are in charge of conducting experimental tests, and some of them are in charge of conducting numerical simulations, 1D and 3D. Well, here on this slide, on the right-hand side, we can see our single cylinder engine with its thermodynamic kit, where we can track the mixture formation and combustion process and also the engine out emissions. For the mixture formation and combustion process, we can use, for instance, visioscope just to look inside of the combustion chamber, and also a fiber optics coupled to the spark plug in order to capture the brightness from the combustion process and detect out ignitions and other problems or issues that we can have inside the combustion chamber for its optimization. And we can also detect the engine out emissions using an external device. Moreover, we have here on the top left-hand side one of our test cell, where you can see an engine coupled to that, and we have on the bottom left-hand side a chassis dyno where we can characterize vehicle performance. Here we can see first on the top right-hand side our combustion lab, and also a fuel characterization lab where we can, for instance, get all the physical chemical properties from a fuel. Furthermore, we have here on the bottom left-hand side our turbocharged test rig, where by means of a combustion chamber here we can generate the enthalpy needed to characterize the turbine and the compressor to get the maps from both. On the bottom right-hand side here we have also a test cell for heavy-duty engines. Okay, and on the top left-hand side here we can have a test room here for one of our test cells. Well, here on this slide we can show you firstly on the top left-hand side the VisioNOC software used to detect from where an out-ignition is coming, and we can also use this to optimize the combustion chamber. And on the bottom left-hand side we can see our numerical simulation lab. Okay, on the right hand side we can see here software and the hardware available for our research. Well, let's go through now our main projects. So this is, I think it happened in 2018, and it was entitled it is entitled Exploring the Limits of Downsized Ethanol Direct Injection Spark Ignite Engine in the different configurations in order to replace high displacement gasoline engines, right? We tested here different hardwares, but we end up with the best, which was the prototype running on ethanol, direct injected, 1.4 liter engine with 2 valves per cylinder, 4-cylinder, and coupled with the twin stage turbo. We got here 44% of maximum brake efficiency at 3,250 RPM. We also achieved the maximum power at of 208 kilowatts at the 5,500 RPM. The mass burn fraction, the 50% mass burn fraction, was achieved at 10.1 crank angle and a 42.5 brake efficiency. Okay. Well, another important work was this one entitled Full Spark Authority in the Highly Boosted Ethanol DC Prototype Engine. This was a work where our intention was to get the MBT at the full calibration map, and we used different strategies to do this, as shown here in the graph on the right side here, the bottom right side. And for the pre-ignition suppression at a very high brake effective pressure, we used firstly at stoichiometric measure, we used the Kula DGR, and then we tried also the water injection to compare both strategies. So the engine used was a prototype engine, 3-cylinder one, okay, turbocharged, direct injected, okay, using ethanol, and also injecting water when needed. So we achieved 65% downsizing capacity using a small scale water injection, and we were capable of replacing a natural aspirated 2.8 liter engines by a turbocharged 1.4 liter engine at 2,500 RPM. This was just to give you an example of the downsizing capacity, right? Another work was the combined effects of internal exhaust gas recirculation and tumble motion generation in a flex fuel direct injection engine. Okay, the intention of this work was firstly to use the EGR, the internal EGR, to reduce pumping losses in order to increase our fuel conversion efficiency, and to recover the burn rate. We used the tumble, to increase the tumble motion to increase the turbulent kinetic energy in order to recover the combustion burn rate, right? Well, very quickly here on the left hand side here, we can see what we have done in order to reduce the internal specific consumption. We started normal here means using the IVO, the intake valve opening of 0. Okay, and in red here we can see another valve timing using 49 crank angle for the intake valve opening, right? Well, so firstly, just increasing the compression ratio with the same valve timing, we obviously increased the gain, the efficiency gain, reduced the internal, the indicated specific fuel consumption, and then we just changed the valve timing. We reduced more 2% the indicated specific consumption, and just using the EGR here, right, and the internal EGR, and then combining with tumble to recover the burn rate, we reduced more 4% in the internal indicated specific consumption. Here we can see that all tests were conducted at MBT. This is very important, so the combustion phase always optimize it. But we've seen here that increasing the combustion, the compression ratio, we obviously decreased the burn rate. This happened because when we reduce the volume of the combustion chamber here, we reduce this is reduced to the cube. and the surface area of the combustion chamber was reduced to the square only. So we have more area to waste heat, and that's the reason because the combustion, let's say, combustion speed decreased. Okay, but when we use it at maximum compression ratio, we used also the tumble to recover the combustion speed. We also got a better result. We recover and also speeded up the combustion more than needed, which was a very good result for us. Well, here another work was the combustion analysis of the SI engine with stratified and homogeneous pre-chamber ignition system using ethanol and hydrogen. So here, as mentioned here, it was a kind of active pre-chamber, right? And in the pre-chamber, we injected hydrogen, just a small amount, okay, around 2%. And we used the ethanol, okay, a lean mixture of ethanol in the main chamber, right, for the stratification. So you can see here when it started homogeneous and when we migrate to stratified, we had a huge gain of burn duration, right, which was really important for the let's say the development. So this was a very important result. And moreover, we can see here, and when we went from a standard engine to stratified, the temperature decreased in all cases, and the indicated specific hydrocarbon emission was higher for the standard engine, and then we had let's say the stratified lower than the standard one, and the homogeneous also lower than the stratified. Well, another work was the misleading total replacement of internal combustion engines by electric motors and study of the Brazilian ethanol importance for the sustainable future of mobility. So here is important to point out that our focus was in let's say the cycle, the entire cycle, not only the application, right? Just to show you, if you take into account the entire cycle, a biofuel sometimes is much better than the electric application, right? We have several pros and cons of both systems, and I'm sure that during the questions I can explain much more about that, okay? But my let's say my intention here is just to call your attention for this, because during the photosynthesis, the biofuels can really absorb a huge amount of CO2 and generate oxygen. This is the only process that generates oxygen naturally. And during the electric cycle, we need to be careful about from where we extract all the materials needed, the raw material, and how we scrap the batteries in other parts, right? This is important, and also the price of the battery and so on. Well, just to talk a little bit about the current projects now and future ones. Our focus is always in the Brazilian renewable energy matrix, right? So we are conducting research with different types of combustion systems. Okay, so pre-chamber using, let's say, active pre-chambers or also passive pre-chambers. We also have been conducting researches with HCCI, homogeneous charge compression ignition, or CAI, controlled out ignition. And we are always looking for innovative and highly efficient combustion systems. Okay, so I'm sure that probably we will have a lot of questions, and I'm available now. Thank you very much, and have a nice day.
Thank you very much for the colleagues from BBEST for the invitation to speak a little bit about electrification by ethanol. As everybody knows, energy is everything. Energy is everything, and energy is conversible. We have used a lot of fossil fuel from the Industrial Revolution on, And this caused the increase, the really very sharp increase of the CO2 concentration in the atmosphere. And this is causing the acceleration of the climate change, with a drastic consequence for the humanity, for the civilization, not so much for the planet, but for our civilization, no question about that. Then this is a consensus that the CO2 is a global problem, A solution for this global problem is the bioenergy. Why? Because with the bioenergy, we can convert the CO2 with the gas in a solid piece of glucose that is made by the insertion of the hydrogen in 6 molecules of CO2. And again, we can convert something that's a gas in something that is solid. CO2 also is a problem for the global warming. It's a very nice molecule. It's not toxic. You cannot make confusion with SO2 and NOx and other components from the smoke. Is extremely beneficial for plants. The more the CO2, the best the growth of the plants. And it's an extraordinary natural battery. Life is actually a CO2 battery. Okay. How can we charge the CO2 battery? Mainly by photosynthesis. With photosynthesis, we can take the hydrogen of the water, put this in the CO2, and 6 CO2, we can make a glucose molecule, and this has a lot of energy that has been collected from the sun and converted in chemical energy. Okay. Another very important point from the glucose is that this molecule can be fermented by yeast, the same microorganisms that make beer, for example, and this can be converted into molecules of ethanol that retain practically all the energy that was in the glucose. Okay. The advantage of this process is that you can convert something that was solid, very difficult to handle with something that is liquid. The beauty of the fossil fuel and why it was spread in civilization is because this is liquid, very easy for transportation and utilization. There is a big fallacy in civilization that is, every time that you see smoke, immediately you say, why, a lot of CO2. It's wrong. The problem is not the CO2 and the solution is not batteries. We have a lot of other pollutants in the smoke, and this is the problem. Battery is not a solution because when you use the battery, it is discharged and you must recharge. And the word nowadays, recharge batteries using fossil fuel. That means instead of putting a local emission, you are going to have a global emission. And CO2 is not a local problem. CO2 is a global problem. Therefore, cars, electric cars that run utilizing batteries that must be recharged with the fossil fuels, there is no sense in this replacement. The point with electric cars is the efficiency of the electric motor. Really, it's much more efficient. However, we must think in economy is in a much broader way. For example, when you look at a combustion motor, we see a lot of peace, and peace means a lot of jobs. Electric cars definitely does not mean battery car. This is completely different. For example, Mirai. This Mirai is a hydrogen car using fuel cell. That means you don't need necessarily big batteries to have this as fuel tank. When we look at the energy density of methyl batteries, we see that it's much lower than the liquid fuels. In addition, when we look at the time, the recharge time for batteries in comparison to fuel time, liquid fuels are much more convenient. And everybody speaks about hydrogen because you have let's say, is not very well coordinated, the electricity production of solar and wind with the electricity need. Therefore, the surplus, the excess of this current could be used to hydrolyze the water, and by this way, we can collect hydrogen. Okay, but is this really green? We don't know exactly what to do with the solar panel, and that can become a big problem. The same way with the wind turbine blades. That means if you don't have the life cycle analysis of this process, you cannot speak really about green. Another point is that the hydrogen after electrolysis must be stored. In storage, hydrogen storage is a very sensitive technology because it's expensive and difficult to handle with. People is trying to concentrate this hydrogen in molecules like ammonia, and more recently, the idea to produce a fuel. What is a fuel? A fuel is you take the hydrogen that comes from the water hydrolysis and put this in CO2. Then you produce linear molecules of carbon full of hydrogen. That means it's exactly what we do with ethanol. Ethanol is an a fuel. Look, when people speaks about a fuel, you don't care anymore about electric motor. This is a combustion motor. That means problem is not combustion. It has always been hydrogen. When we look at the molecule of glucose, the hydrogen is in the hydrogen that we have the energy we use. When you look at oil, hexane, for example, that could come from glucose, this again, the energy is in the hydrogen. We see in the oil a densification of the energy, has much more energy than glucose. However, this is exactly the same kind of material, the same kind of branch, let's say, a kind of gray branch, more dense. However, at which cost we have this densification? When you look at the gel against the biometabolism, we have here the glucose, we have the planet, and then you have the hexane with this energy. We can take the yeast, make fermentation, then you have the ethanol with this energy. But look at the time. We need here millions of years to produce oil, while in few hours we can have ethanol. That means the balance is to have 60% of the energy of oil. We can use 1/1000th of time to produce a relatively similar amount of energy. That means it's logical to utilize the ethanol instead of oil. And how to use this hydrogen branch? We have made combustion to have combustion engines. However, nowadays, with this fuel cell technology, we can utilize these molecules, this hydrogen, to produce electricity. We see then that combustion is not a problem because this car here is the most efficient car that we have now in the world, and this is a hybrid flex that can work with ethanol. The problem then is not combustion, the problem is this combustible, that means the fuel that you use. Then when we look at the different technologies in the utilization of the different fuels, we see that the sustainability is not in the fossil, and the combustion with ethanol is great, is really not bad, better than hybrid with using gasoline. However, when we have the hybrid using ethanol, is much better than the battery car in Brazil, utilizing a very, very good sources of electricity. When you look at Europe here or US, the situation is much better, much more favorable to ethanol. The best-selling cars in the world, when we take a look in the cars that are sold in the world, we see that it's not popular cars that are the most sold, the best-selling cars. On the contrary, are these big trucks, and the Ford and the other companies are converting these trucks to electricity, and these trucks have been converted. The consequence in Brazil is the massive layoff, not only in Brazil, but in a lot of countries in the world, because technology is concentrated in the developed countries. However, we have here an opportunity. Ford just released this Transit, this model of hybrid car, big car. The autonomy is 500 kilometers. Consumption is really very good. It's great, wonderful. Relatively less emission of CO2, however, it's gasoline. If you convert this to ethanol, the improvement is great. And this is what we should do in Brazil. Instead of closing the company, just produce these hybrid cars using ethanol. I think a huge opportunity. The politics should go in this direction. Okay, however, we see that the fuel electric is really sexy. We see Tesla, it's a kind of religion with a lot of heart instead of brain. And when we look at the Tesla carefully, again, we need oil to produce electricity to run the car, not at the during the movement, but somewhere this CO2 is emitted. The real green hydrogen, however, can come from the ethanol. When we mix this with water and utilize reformers, we can really produce CO2, that is a green CO2, and green hydrogen. Green hydrogen, really green. We see here the electrons and the protons. And when we produce this hydrogen, this new technology named SOFC, that is not so new, but now become more popular, and Brazil, in my opinion, should have really a very intense research and development in this area. How it works? We have here the hydrogen, the green, real green hydrogen, and this hydrogen in the anode, the electrons are separated from the protons, and the electrons have this barrier here, cannot go through the SOFC membrane, the SOFC material. Then it goes to the wire and makes an electric current. On the other side, the oxygen comes, receives the electron, becomes an anion, and this anion is able to go through the membrane, and on the other side, join to the hydrogen to produce water. That means great, clean, green. This is how it looks like a new motors. These are the gas processing unit. Here is the stack, the fuel cell, really. Here we have an equilibrium between brain and heart. This is full electric, but utilizing ethanol to produce electricity. This is not a dream. This is a real car, a real prototype that ran in Brazil for around 2 years with over 26 kilometers per liter of ethanol. We have created now an innovation team really to push all this technology. Amazing people that are here. I don't have time to present everybody, but people with a lot of experience that has already developed ethanol, flex cars. Here, the guys from AVL working on the fuel cell. In the university, we have top people working all this area. Here, we from our laboratory, the LGE, we do believe that this is the most important part of the train. If you don't have this locomotive, if you don't have this motorization at ethanol, there is no reason to produce biomass. And if you don't produce biomass, we have really no real solution for climate change acceleration. This is the team of the lab. This is the team in pandemics. It is the future that we believe. Thank you very much for attention.